What if I told you that deep learning isn't a completely different technology? It's actually a subset of machine learning, and yet people often use them as if they are competitors. So, what's the real difference? In this video, we'll break it down visually, mathematically, and intuitively. By the end, you will know exactly why traditional ML still dominates some problems, while deep learning powers today's AI revolution. Both machine learning and deep learning starts with data and end with predictions, but the journey is completely different. In traditional ML, you first design the important features yourself, things like averages, edges, or statistical patterns. Then, a relatively shallow model learns from those features. Deep learning skips that manual step. It consumes raw images, text, or audio and automatically learns increasingly useful representations through multiple layers. That's why ML shines on structured data, while DL dominates unstructured data. Think of a traditional ML model as making one major transformation before predicting the output. Deep learning, however, stacks many layers together. Every layer extracts a slightly higher level representation. For an image, early layers detect edges, middle layers combine them into shapes, and deeper layers recognize complete objects. This hierarchy is learned automatically during training. The trade-off? Millions or even billions of parameters require GPUs, more data, and significantly more compute than classical ML. The biggest difference isn't just the architecture, it's how the models learn. Many classical ML algorithms solve a relatively simple optimization problem, and some even have direct mathematical solutions. Deep learning can't do that because millions of parameters interact across many layers. Instead, it performs a forward pass to compute predictions, measures the error, then uses backpropagation and gradient descent to send corrections backward through every layer. This process repeats thousands of times until the network converges. At first glance, a neuron looks similar to a simple ML model. Both multiply inputs by weights, add the bias, and compute a value. But their purpose is different. In many ML algorithms, that computation directly produces the final prediction. In deep learning, each neuron is just one tiny building block. After the weighted sum, an activation function like ReLU introduces nonlinearity, and the output is passed to the next layer. Millions of these neurons work together to learn highly complex patterns. Imagine building an image classifier. In traditional machine learning, you manually extract features such as edges, corners, textures, or HOG descriptors before training the model. CNNs eliminate this manual engineering. Instead, a small convolutional kernels slide across the image and learn the most useful filters automatically. These shared kernels detect patterns regardless of where they appear, making CNNs both efficient and incredibly powerful. As layers stack together, they gradually capture increasingly complex visual features. Every approach has weakness. Classical machine learning often struggles when the model memorizes the data instead of learning general patterns, a problem known as overfitting. Deep neural networks face a different challenge. During backpropagation, gradients can become extremely small as they move through many layers, making early layers learn very slowly. This is called the vanishing gradient problem. Modern architectures and activation functions reduce this issue, but understanding it explains why training deep networks isn't trivial. Learning isn't just about fitting the training data, it's about performing well on unseen examples. Classical ML uses techniques like L1 or L2 regularization to discourage overly complex models. Deep learning goes further with methods such as dropout, batch normalization, and data augmentation. These techniques prevent neurons from becoming overly dependent on one another and improve generalization. Different tools, same objective: reduce overfitting and make the model reliable on real world data. So, when should you choose each approach? If your dataset is structured, relatively small, and interpretability matters, traditional machine learning is usually the better option. It's faster to train, requires fewer resources, and often achieves excellent accuracy. But when you are dealing with images, speech, videos, or natural language, deep learning has a huge advantage because it learns complex representations automatically. The choice isn't about which is better, it's about which matches your problem. Before jumping into deep learning, ask three questions. What type of data do you have? How much data is available? And do you have enough compute to train a large model? If the answers point toward structured data and limited resources, machine learning is often the smartest choice. If you have massive unstructured datasets and GPUs, deep learning can unlock capabilities that traditional ML simply can't achieve. The right tool depends entirely on the problem. Here's the key takeaway: deep learning isn't replacing machine learning, it extends it. Both optimize parameters to learn from data, but they differ in how features are created, how models are structured, and how learning happens. Machine learning relies more on human expertise, while deep learning learns representations automatically through deep neural networks. Understanding this distinction is the foundation of almost every modern AI system you'll encounter next. Thanks for watching, and I'll see you in the next one.